lecture 1.2, state variables, and state equation. The problem solving strategies of thermal are similar to kinematics. So to give you a sense of how thermodynamics work, I want to use an analogy of kinematics. And I can say here that kinematics is the mathematical structure to understand. It's the mathematical structure of motion, which means if you want to understand motion, you got to go through kinematics. And there's typically a three-step process. We define a system. Once we know the system, we need the variables that then explain what we mean by motion. And then finally, we put this all together with the kinematic equations. So let's go through that. So the first thing that we have to do is we define the system. So when we define a system, what we typically do here is that we imagine that we have a car. Or I could have a block. It doesn't really matter. So if I have my car, a car is an extended object. So we take our system as the car here, and then what we do here is that we try to make this system as simple as possible. In other words, we pick the center of mass. And the car is not an extended object anymore, but in fact, it's now a point. It's the center of mass point. So now that we've defined the system, then what we need to do here is that next, we look at the variables. In fact, we should call them the motion state variables. So when I look at the motion state variables, we know that there are four variables. That is t, x, v1, v2, and acceleration. So if one of these variables changes, then we have the following thing. So if they change, I could have acceleration equals to 0, which means then I have constant velocity. If I have acceleration that's not 0, then I have a situation of changing velocity, which of course means acceleration. So what happens here is that by looking at this thing, if a variable changes, then that means that the system changes. That's how we define our state variables of motion. And then finally, we have our state equations. So if I look at my state equations, what they do here is that they govern how state variables are connected. And we have three kinematic equations. We have the final velocity equal to the initial plus acceleration times time. The final velocity squared, v1 initial squared, plus 2a delta x. And then finally, delta x is equal to v1 initial times time plus 1/2 at squared. Those are our state equations for motion. Now what I want to do now is that I want to apply the same process to physics 4C thermodynamics. So that means we got to go define our system, our variables, and then our equation. So let's follow this process. So I'm going to call these primes instead. And we need to define the system. Since thermodynamics is the energy transfer of materials, then we're going to ask the question, what is the simplest possible material? Of course, we have gases, liquids, and solids. So if I look at gases, liquids, and solids, the easiest one has to be the gases. As a consequence, we then pick the simplest material as the ideal gas is the simplest, just like the center of mass and motion. In other words, if I have what's called an ideal gas, there's nothing very special about the ideal gas. That means if I want to use energy arguments, then that means here is that the only thing that happens with ideal gases is that they're just point particles. There's no bonding. And if there's no bonding, that means that there's no electrical potential energy. And if there's no electrical potential energy, then that means that potential energy is zero. But if I have a non-ideal gas, then I have to worry about bonding. In this situation, I can imagine that I have two molecules that bond together. So when I look at their motions here, their motions are similar to the ideal gas, but the big difference here is that there is electrical bonding. And if there's electrical bonding, we have to now include the potential energy into our equations. So the energy structure of ideal gases is completely described by its kinetic energy, its microkinetic energy, and nothing else. So if I look at the energy of the system, that is its internal energy, which is the same as the microkinetic energy, then because there is no bonding, we can see here immediately that that does not contribute into our energy equation. So therefore, the internal energy is only described by its micro potential energy and nothing else. I think I said micro potential energy. I meant kinetic energy. That is a big deal. To not have electrical potential energy in this process really simplifies the problem quite a bit. Now, let's go define the thermal state variables. So we need a set of variables that tell us how a thermal system changes according to K micro. And what we find here is that there are 4 variables. We have volume. I mean, that's pretty easy to define. We have temperature. Temperature turns out to be more complicated. And then we need the mole number. That tells us about how many particles are in the system. And then we need to talk about pressure. So if I have these 4 variables, then that means here that a state is completely defined by these variables right here. In other words, these are our state variables for an ideal gas. And what this really tells us is this: if a system changes, we will know it because one of these variables has changed. In other words, if the pressure changes, we're going to know it, and therefore the system has changed, as well as the temperature, as well as the volume, and as well as the number of particles within the system. The state equation in thermal is the mathematical equation that connects pressure, temperature, volume, and the mole numbers together. So the state equation is a mathematical equation that connects pressure, temperature, volume, and mole number together. this is called the ideal gas law. And because we're going to use this phrase a fair amount, I'm going to use the acronym IGL. And it says this, that the pressure times the volume is directly proportional to the number of moles times the temperature. This is the ideal gas law. In other words, what this is really saying here is that the ratio of the pressure volume times the number of moles times the pressure, this is equal to some constant. So let's define each of the variables. Okay, so let's define each variable of the ideal gas. So the first one here, which is the easiest, is the volume. We all know what a volume of a container is. So the volume that contains an ideal gas, if I didn't have a container, the ideal gas would just move away. So when I look at this thing, I could say that here's my container. And inside this container, I have gas particles that are randomly moving with some microkinetic energy. And so when I look at this, the units of volume, the SI units is in meters cubed. And that turns out to present a problem in calculations for numerous students here. The second easiest thing to define is the temperature. It turns out that of all of the state variables, temperature is by far the trickiest. So the classical definition of temperature is it's proportional to the average, and this is a unique average. This average is actually called the RMS value, and we'll get more on this in chapter 3, but it's the RMS average. But most of the time I just call it average. It's proportional to the average kinetic energy of a gas particle. In other words, temperature, defined classically, is proportional to K average. So because of this, we could then say that if we talk about the word temperature, which is of course capital T, this really tells us that if I have a higher average kinetic energy, then I'm going to have a higher, I'm going to run out of space, so I'm going to move this, right? I'm going to have a higher temperature. If I have a lower average kinetic energy, then that means I'm going to have a lower temperature. Now, the units of temperature are known they're still SI units, but it's known as the absolute temperature scale. So the units of temperature are in Kelvin, which are written K. There's no degree. And this is known as the absolute temperature scale. Why is it called the absolute temperature scale? Because at absolute zero, which is 0 Kelvin, there is no theoretical motion possible. There is an important conversion between degrees Celsius and Kelvin, which is 273. So the next one that we should look at is that we should look at the number of moles, which is defined as little m. So the number of gas particles in a sample is measured via the number of moles. So if I look at the definition, we say that 1 mole is the number of atoms in a 12-gram sample of carbon-12. So if I center that, that is our definition of a mole. So it turns out that for carbon-12, there are 6.022 times 10 to the 23 atoms in 1 mole. And the way we display this is we talk about a number called Avogadro's number, which tells us they define it as Na, and this is equal to 6.022 times 10 to the 23 atoms per mole. So this number will continue to pop out while we study thermodynamics. And this is the SI unit, and this SI unit essentially tells us how much stuff is in a sample. Now, when you look at Avogadro's number, what you find here is that it typically refers to atomic substances, not macroscopic objects. You can have a mole of eggs or golf balls or whatever you want to talk about, but people don't really look at it this way. And in fact, you should check out a humor link and this is XKCD, and this is a mole of moles. And this will tell you just how gigantic 10 to the 23 is. So now let's get down to trying to understand here. So what we want to do here is that we want to comprehend the largeness of Avogadro's number. Avogadro's number is so large that it is impossible to comprehend its largeness. And here's some values that people have mentioned in the past. So the first thing is that if one collected all the leaves from every bush and tree in the world, 10 to the 24 is larger. Think about that. Collecting every leaf from every tree, bush, and plant in the world, 10 to the 24 is larger. Another commonly referenced is if you were to collect all the drops of water from every river and lake in the world, 10 to the 24 is larger. Note that I did not talk about ocean here. There's actually more drops of waters in the world's ocean than Avogadro's number by a factor of 1,000. Because this is almost impossible to really understand, I want to do a concrete example so that you see that I'm not making this up. So here is the length of a mole of water molecules. So, of course, when we talk about water molecules, it's H2O. So what I want to do here is that we need to use the periodic table. And what we find here is, of course, is that if I have hydrogen and I have oxygen, here's what we see here. So from the periodic table, we see here is that the molar mass of hydrogen is 1, the molar mass of oxygen is 16. So by the way, this is 16 grams per mole. So that means in 16 grams of oxygen, there is Avogadro's number of oxygen molecules. So then what we could say here is that the molar mass of water is, because it's H2O, that means I have 2 hydrogen masses plus 1 oxygen mass. And if I look at that, that's going to be 2 times 1 plus 16. So this gives me 18 grams per mole. And that gives me the molar mass of hydrogen, or excuse me, of water. So really, the question should be this: what is 18 grams of water? It turns out that it's just over a tablespoon. So it's just a little bit bigger than a tablespoon. So then we have to start going through our process here. So then I'm going to ask the following question. How many water molecules are there in 18 grams of water? The answer is it has to be Avogadro's number, which we can approximate as 10 to the 24 water molecules. So now, if these 10 to the 24 water molecules are lined up linearly, how long is this chain? Well, so here's what we know. So if I look at a water molecule and I look at its hydrogen atoms, it's going to look something like this here. So this is going to be hydrogen, and this is going to be oxygen. It turns out that this is going to be positive, and that's going to be negative. So when I look at the diameter of this water molecule, it turns out that its diameter is equal to 3 times 10 to the minus 10 meters. So now if I have a chain of 10 to the 24 molecules, what that means here is that I'm going to have, let's say I'm going to have 1, 2, 3, and then this is going to be 10 to the 24. And if I start to add these guys together, here's what I'm going to see. So in this case here, we know that this is 1, 2, 3, and I line up all 10 to the 24. The question that we're asking is, what is the length of this chain? Well, we can compute that. So this distance is then going to be delta x, which will be the diameter of water times the number of water molecules. And we already know that this is going to be 3 times 10 to the minus 10 times 10 to the 24, which then gives us 3 times 10 to the 14 meters. That is the distance or the length of this chain of water molecules. Now, 10 to the 14, I mean, I really don't know what that is, right? We could ask, so how large is 3 times 10 to the 14 meters? That's really the question now. And the way we answer this question is that we need to compare it to the Earth Sun distance. And if you do that, what we know here is we have our pale blue dot, and then we have our yellow sun as viewed from Earth. So here's Earth, and here's the sun. It turns out from center to center, that's about 10 to the 10 meters. So if you start to compare these two lengths here, then we could say here is that the length of 1 mole of water, that is the length of all of the water molecules in something over, a little bit bigger than a tablespoon, divided by the Earth Sun distance. This is then 3 times 10 to the 14 divided by 10 to the 10, which is equal to 30,000. Think about that. That is insane. The length of all water molecules in a tablespoon is long enough to go back and forth between the Earth Sun distance 30,000 times. What can I say? As I stated earlier, Avogadro's number is not comprehensible or comprehensible, right? How do you comprehend that? So now that we've kind of talked about this, let's step away from this thing. This is not the way we envision Avogadro's number. So the way we use Avogadro's number is to calculate mole number from molar masses. So here's what I mean. So the number of moles, by definition, is also be the number of particles in a sample, and then we look at the number of particles in a mole, and that is then the number of sample particles divided by the number of particles in a mole. This is one way that we can define the mole number. this becomes useful in the third chapter, but not here. So the most useful form involves masses. So if I take Avogadro's number, or excuse me, the mole number, we know that this is the number of the sample divided by Avogadro's number. But now if we multiply this by the mass of the sample, divided by the mass of the sample, you could see I'm not changing this whatsoever. This gives you the mass of the sample divided by the molar mass. And this gives you the mole number right here. This is by far the most efficient way. So in problem solving, you'll find that this is usually given in problems. This, on the other hand, you look up in the periodic table. Now I'll do my first example, 1.2 or 1.1.